now let's talk about distributed storage, and we're gonna cover this sort of in a detailed manner. Okay, so as we mentioned, we chose TIKB project to sort of act as our storage layer. And so TIKB is a graduated project of the Cloud Native Compute Foundation, and it's originally created by PinCap to complement TIDB. It's a highly scalable, low latency, and easy to use key value database that delivers performance in less than 10 milliseconds at any scale. TIKB is intended to fill the role of a unified distributed storage layer and excels at working with large-scale data by supporting petabyte-scale deployments spanning trillions of rows. The TIKB cluster consists of the following components: a group of nodes to store the key value data. Each node is a physical server. A group of placement drivers that work as a manager of the cluster. It can be a group or a single placement driver. It can be 1 or 3, depending if you need high availability or not. And a set of clients that let you connect to a cluster and use either the raw key value API or the transaction API with transactional consistency guarantees to access and update your data. Clients interact with the placement driver through GRPC. Okay, so let's talk about GRPC. Communication between services occurs over remote procedure calls, also known as RPC. As a distributed system involving a number of nodes, TIKB cluster uses RPCs to communicate between nodes, as well as the placement drivers and clients. So it uses pretty much gRPC everywhere. The interface language format is protocol buffers, also known as protobufs, which is a common practice with gRPC communication. gRPC does a great job wrapping up these technologies right here, which we'll talk about, or all of the technologies used in the cluster, or TIKB technology, so to speak, and providing a useful interfaces. So here, the communication in most layers, or all of them, is gRPC, or the network communication. Now let's talk about distributed transactions. A database transaction, by definition, must be atomic, consistent, isolated, and durable. Database practitioners often refer to these properties of database transactions using the acronym ACID. So we usually call these ACID transactions. Transactions provide, transactional processes or operations provide an all or nothing proposition, which means each work unit performed in a database must either complete the workload in its entirety or have no effect whatsoever. Furthermore, the system must isolate each transaction from other transactions. Results must conform to existing constraints in the database, and transactions that complete successfully must get written to durable storage. A distributed transaction is a database in which 2 or more network hosts are involved. Now imagine the problem or the situation where 2 clients modify the value of a key at the same time. For this particular problem, TIKB uses MVCC, which is known as multi-version concurrency control, to prevent deadlock and performance problems. Without MVCC, the data would need to be locked. So MVCC leverages data versioning by appending a version number to each key that is written. Versions with larger numbers are placed first. In this way, you can directly locate the first position to consume the last successful write, or a particular data version, if so specified, if you specify a particular version. Usually, hosts provide transactional resources, while the transaction manager is responsible for creating and managing a global transaction that encompasses all operations against such resources. Distributed transactions, as any other transactions, must have all 4 ACID properties. So distributed transactions are for the distributed transaction layer, a common algorithm for ensuring correct completion of a distributed transaction is the two-phase commit, also known as 2PC. In this case, TIKB adopts Google's Percolator transaction model, which is a variant of the 2PC, two-phase commit. So an optional configuration is the Asynchronous Commit API. So usually a client must wait for the commit to complete if we're using a two-phase commit synchronously. If the application is very latency sensitive and the transaction does not involve many keys, one can optionally enable a sync commit option. When a sync commit is used, the transaction will return a successful commit to the application as soon as the first stage of pre-write is completed. So there's less latency overall. The cost or the cost of this is that if we encounter a failure while writing, the transaction is more costly to recover. So a good rule of thumb is to select the default async commit key limit to 256 keys in any given batch. So if a batch transactions are over this limit, if a batch is over 256 keys, it may be a better option to just use regular two-phase commit, or not enable this option per se. So we already talked about the transactional layer and maybe why it could be important, or in what scenarios it could be important. So usually these scenarios are more expensive, computationally speaking, but they're generally a requirement for, let's say, financial institutions or sensitive government agencies that require the transactional properties, and many other use cases. Yeah. So let's talk about the raw key value API. Raw key value API is a lower level API to interact with data directly without going through the transactional sort of model. If our application requires low latency and does not necessarily involve transactional operations, this can be which is usually a typical use case for analytical workloads. We can just go ahead and leverage the raw key value API. So for our particular scenario, we're only going to be interacting with raw key value API because we're running analytical workloads for analyzing chemical data sets. Now let's talk about the Raft consensus algorithm and how it works with TIKB. So the TIKB cluster replicates data to multiple machines, which ensuring data consistency and tolerating and ensuring failure toleration or fault tolerance. Let's just call it that way. Data is written through the interface of Raft instead of directly to RoxDB. So RoxDB is going to be the actual data. We'll cover it in the next slide. But whenever we instead of writing directly to the data, we talk to the Raft API so that we can have a consensus sort of layer. So TIKV becomes a distributed key value storage, which can automatically recover lost replicas in case of machine failure and keep replications and applications unaffected. Sorry. So yeah, the Raft algorithm, it's a little deeper than this. It usually has to do with having a Raft master and sort of having a consensus of what the state of the cluster is in general. But for this particular use case, it's ensuring data consistency, which means at a super high level, let's say that we write 3 copies to the RoxDB layer, 1 on each node, and let's say that this middle node is the Raft master. So each Raft group generally has a Raft master, or will have a Raft master. So our cluster right now says, okay, let's write. So we're going to write 1 copy to this one, 1 copy to this node, and 1 copy to this one through the raw key value API. This raw key value API is going to talk to the Raft master. It's going to tell it, hey, I want to write to, or I want you to write to the RoxDB underlying layer, to the actual data I want you to write. And Raft is going to say, okay, let's write it. So let's say that this node number 1 is going to start writing the data. But let's say that it's taking a long time. That something is wrong with this node. It's taking a long time. Node 2 is also going to write the second copy of the data. And let's say that this completed in 1 second. It's already completed. And let's say that the node 3 is also completed. It's successfully written the data to here. So Raft consensus means that whenever you have a majority that have successfully performed the operation, the Raft layer can successfully report a successful write per se, even though this node has not successfully written. And that's because the general consensus of the cluster says that we've already successfully written to this particular data to the node. So that's consensus, maintaining the cluster state of the state of the cluster. Okay. So RoxDB. RoxDB is a persistent key value store for fast storage environment. Here are some highlight features from RoxDB. So it uses a log structured database engine written entirely in C++ for maximum performance. Keys and values are stored just as arbitrarily sized byte streams, so byte format. It's optimized for fast, low latency storage, such as flash drives, high-speed disk drives. RoxDB exploits the full potential of high read-write rates offered by flash or RAM. So it can also work on in memory. It is adaptable to different workloads, from database storage engines such as MyRox to application data caching to embedded workloads. RoxDB can be used for a variety of data needs. It also provides basic operations such as opening and closing a database, reading and writing to more advanced operations, such as merging and compaction filters. And yeah, I think it also has a Bloom filter in there, which is interesting. Okay, so let's talk about the physical data. So this is a TIKV cluster. We have a placement driver which acts as a cluster manager, which periodically is going to ping or pull each of these nodes to check replication constraints and maybe balance data automatically, just based on let's say that it finds that this node has enough like 80% utilization, and these nodes have 30% storage utilization. Then placement driver will constantly ping each node to kind of rebalance the data evenly, automatically also. So region is the basic unit of key value data movement. Each region is replicated to multiple nodes. These multiple replicas form a Raft group. The store. There's a RoxDB within each store, and it stores data into local disk. We'll talk about this in a further slide. And a node, which is a physical server or machine. So let's cover the placement driver, which is also in charge of scheduling. So as a manager in the cluster, the placement driver provides the following functions. It has a timestamp oracle, which plays a significant role in the precolator transaction model. Remember, we talked about the two-phase commit model. So placement driver implements a service to hand out timestamps in a strictly increasing order, which is a property required for the correct operations of the snapshot isolation protocol. And then it also acts as a region scheduler, which is, something common to distributed systems, the scheduler. So in the case of TIKB, so data in TIKB is organized as regions, which are replicated to several stores. The placement driver, as the region scheduler, decides the storage location of each replica. So we talked about maybe it found that certain nodes still have enough capacity left, and it might decide, okay, this node, schedule that data load to this right over here. So it decides the storage location of each replica. The placement driver collects cluster information from store heartbeats and region heartbeats, and then manages scheduling plans from the information and strategies. So it's gonna collect heartbeats from it's gonna periodically pull these components to kind of analyze their to perform health checks, just to see how they're doing, and maybe detect failures or for rebalancing purposes and whatnot. So scheduling plans are a sequence of basic operators. Every time a PD receives a region heartbeat from a region Raft leader, so Raft group will always have a leader. It checks whether there is a pending operator in the region or not. Sorry, a region. It's going to check whether there is a pending operation in the region or not. If the placement driver needs to dispatch a new operator to a region, it puts the operator into a heartbeat response and monitors the operator by checking follow-up region heartbeats. Note that here operators are only suggestions to the region leader, which can be skipped by regions. Leaders of regions can decide whether to skip scheduling operator or not, depending on its current status. Okay, so yeah, but basically the at a high level, this placement driver, again, it's just going to ping each component, maybe let's say every 5 seconds or whatever interval, and it's just going to analyze the health, and then based on that, it'll sort of determine if any action is needed. Now, let's talk about region, peers, Raft groups, and region splits. So what's a region? A region is the minimal piece of data storage in a TIKB cluster. Each region represents a range of data, which holds up to 96 megabytes by default. 96 megabytes per region. For each region, each replica is also known as a peer. And each peer is stored in different stores. So this is intuitive for fault tolerance reasons. Let's say that if you store region 1 and on the same node and you lose node 1, that's going to be a design sort of flaw. So yeah, you need to have them physically separated if possible. Peers. Each region has 3 replicas by default. A replica of a region is called a peer. Raft group. Multiple peers of the same region replicate data via the Raft consensus algorithm. So peers are also members of a Raft instance. TIKV uses multi-Raft to manage data. That is, for each region, there is a corresponding isolated Raft group. Region split. Regions are generated as data writes increase. The process of splitting is called region split. The mechanism of region split is to use one initial region to cover the entire key space and generate new regions throughout splitting existing ones every time the size of the region or the number of keys has reached a threshold. So we said maybe if the size of this region reaches more than 96 megabytes, it'll perform a region split. It'll partition the data. Okay, so that's sort of distributed systems at a high level in general, per se. And so distributed storage systems. In this case, TIKV, and they have a pretty good, a well-defined architecture. So it's a good distributed storage architecture. It's been thoroughly planned, and it seems to have all the core components that a system such as this must have. Let's just say like the scheduler. It even goes beyond the traditional sort of cluster by having these Raft sort of interfaces and whatnot. So it even makes it more efficient with RoxDB. So it's a pretty cool architecture that they have. Okay,